Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. And of course, please subscribe if you like what I'm doing, because that's the new way you can keep me going, refreshed, and inspired. Example 65F, determine the maximum live shear and moment at sea by the moving loads shown. So these are a series of loads and this is the beam. So let's develop formula basically, not by the qualitative or the shortcut, but we'll just check using the shortcut later. So for shear, it is expected to look like this, where the maximum would be at the left. So let's call this R1, then R sub 2. So let's have the unit load at any position, then its distance from the left as x. So its distance from the right is 20 minus x. So let's develop expression for R1, summation moment C equals 0. So R1 times 10 equals 1 times quantity 20 minus x. So R sub 1 therefore is 0.1, 1 over 10 or 0.1 of 20 minus x. Then let's draw free body diagram for developing shear at C. So from left to this point C, the positive shear is going down. Then positive moment is counterclockwise. That's the designation. And that distance is, because this is 10 plus 5 and that is x, so this is 15 minus x. So shear at C is R1 minus 1 for 0 less than equal to x less than 15. So that's the condition for shear. Substituting the value of R1, which is 0.1 quantity 20 minus x minus 1, then that's the shear at C for 0 less than equal to x less than 15. Then when x is greater than 15, this unit load is no longer part of the free body diagram, so this minus 1 will be removed. So the expression will become 0.1 of 20 minus x only. And that is for x greater than 15. So if we plot for shear when x is 0, this is the formula. 0.1 times 20 is 2 minus 1, so it is positive 1. When x is 10, 0.1 times 20 minus 10 is 1 minus 1, so it is 0. When x is 14.9999, just to the left of C, so this is still applicable formula. So 0.1 of 20 minus 14.9999, that's about 15. So 0.1 of 5 is 0.5 minus 1 is negative 0.5. And when x is 15.0001, or just to write this the formula, so 0.1 of 20 minus almost 15 is 0.1 of 5, and 0.1 of 5 is 0.5. And finally, when x is 20, shear at C is 0. So it checks the qualitative influence lines. So that's the expected influence line, and that's the ordinate. So M sub C, on the other hand, is summation moment at C equals 0, R1 times 5 minus 1 times quantity 15 minus x. So substituting the value of R1, which is 0.1 of quantity 20 minus x times 5 minus 1 times 15 minus x. So N sub C is 0.5 quantity 20 minus x minus 1 times 15 minus x. And this is applicable for 0 less than equal to x less than equal to 15. Then when x is exactly 15 and greater than 15, this part is no longer part of the FBD. And this will also be 0 when x is 15, or this is removed. The moment contribution of 1 is no longer part, so this contribution of 1, the unit load, will be out. So what remains is this 1.5 of 20 minus x for x greater than equal to 15. So if we plot when x is 0, 0.5 of 20 is 1, oh sorry, 10, then minus 1 times 15 minus 0, so 10 minus 15 is negative 5. Then when x is 10, 0.5 of 20 minus 10 is 5, minus 1 times 15 minus 10, so minus 5, it is 0. So this is the expected influence line for moment qualitatively. Then when x is 15, so 0.5 of 20 minus 15, 0.5 of 5, 2.5. And when x is 20, this is 0, so it's 0 here. So it checks the shape of the influence line for moment at C. So therefore, the maximum values for shear would be when these loads will enter somewhere here, because the ordinate is greater. So we will also find the ordinates at 2 meter increment, because this is 10. So the possible maximum shear one is 100, when only the 100 load is over this point, and ordinate is 1, so that's 100 kilonewtons. By the way, for 2 meter increment, this is 0.8, because the distance of this point from the right here is 8, so that's 0.8, and another 2.6, 0.4, 0.2, and 0. So by similar triangles. Likewise for moment, negative 5, this is negative 4, negative 3, negative 2, negative 1 by similar triangles also for every 2 meter increment. So for example, y as to 2 equals 1 as to 10. So that's why it is 2 times 1 over 10 or 0.2 the ordinate here. Same is to here. Y as to 2 equals negative 5 as to 10. Negative 5 over 10 is negative 0.5 times 2. So that's why you have negative 1 here. And because it's obvious, I just put this immediately. So when only the 100 kilonewton is over here, the 60 and the 40 kilonewtons load are still on the span. So the maximum possible shear 1 is 100 times ordinate 1, so 100. When the 100 kilonewton load is moving 2 meters, here position the ordinate is 0.8, then the 40 kilonewton load is over this point, only the two loads are still on the span, so V sub C2 is 100 times 0.8 plus 40 times 1. The ordinate of 40 will be 1 because it is here. So the second possible maximum shear at C is 120 kilonewtons. When all the loads are on the span, the 60 kilonewton load is over here. The 40 kilonewton load will be here, 9 meters from this support. So its ordinate is, because the distance is just 1, the ordinate of the 40 kilonewton load would be 0.9 between 1 and 0.8. And the 100 kilonewton load will be 7 meters from here. So it is here. This is 7, and the ordinate is between 0.6 and 0.8, so it is 0.7. So therefore, V sub C3 is 100 times 0.7, because the 100 kilonewton load will be over here. So 0.7 plus 40, 40 would be 9 meters from the right. So the ordinate is 0.9 plus 40 times 0.9. Then the 60 kilonewton load will be over this end of the beam, and the ordinate is 1. So plus 60 times 1. Therefore, V sub C3 is 166 kilonewtons, because this is the maximum value of all possible load positions, then that's the maximum shear at C. So V sub C max is 166 kilonewtons. Then for maximum moment, again, when the 100 kilonewton load is over here, the ordinate is negative 5. So M sub C1 is 100 times negative 5 is negative 500 kilonewton meter. When the 40 kilonewton load is over this point and the 100 kilonewton load is to the right of it 2 meters from this left end or 8 meters from R1, the ordinate under the 100 kilonewton load will be negative 4 and the ordinate under the 40 kilonewton load is negative 5. So MC2 is 100 times negative 4 plus 40 times negative 5, and it is negative 600 kilonewton meter. Finally, with all the loads or the span, the 100 kilonewton load will be here. The ordinate is negative 3.5. The 40 kilonewton load will be here, 9 meters from the support R1, and the ordinate is negative 4.5, and the 60 kilonewton load will be here. The ordinate is negative 5. So MC3 is 100 times negative 3.5 plus 40 times negative 4.5, then plus 60 times negative 5. And MC3 is equal to negative 830 kilonewton meter, because again this is the maximum value. Then MC max is 830 kilonewton meter and it's negative. So 830 kilonewton meter. So that's it for this problem. I hope that you were able to follow the solution.